Okay, so let me just repeat the just a few instructions here. So please turn off mics and webcams. Then here is the poster, the flyer of the school, and at the bottom right here, you have the link to the YouTube channel where you can find the presentations. So we're only missing yesterday's presentations, and we'll be putting them online later today. And so now we have the pleasure of having Ricardo Lobo from ESPCI. And so he will be the speaker of the morning session today. And what I would like to do before giving him control of the meeting, I would like to just say a few words about Ricardo. So let me stop the sharing. We don't need that. Okay, so I will say something that Ricardo loves to tell, but this time I will be the one telling it. So Ricardo Lobo, if you look on Wikipedia, is a Brazilian football striker, football meaning soccer for the American crowd, who plays for a club in Cyprus. But as it turns out, our speaker of today is not this one, but the Ricardo Lobo, who studied at the Federal University in, I guess, Minas Gerais in Brazil, and obtained a PhD in optical properties of conducting oxides back in 1996. Then Ricardo postdoced on time-resolved infrared spectroscopy at Brookhaven National Lab, on pump probe at the Free Electron Laser Facility in Orsay, and on optical properties of cuprates at ESPCI, where he eventually got an appointment from CNRS in 2002. More recently, Ricardo became the head of the, let's say, quote unquote, condensed matter department at ESPCI. Technically, it's called LPEM. And he started his appointment in 2014 until, was it last year?
Yes, yes, I just
yeah, I know. You counted the, you had the clock counting time backward.
Yeah.
So I remembered last year. And he is currently a CNRS research director. In 2008, he was awarded the prize, the Ludwig Gensel Prize. Yeah. And now I will let Ricardo speak, and he can share his screen with you. Thank you, Ricardo.
Thank you very much, Mark. As you notice, soccer in Cyprus doesn't pay well, so I have to reconvert myself to physics. Thank you very much for this introduction. I'd like to thank all the organizers, Mark Gabet, Masashi Kawasaki, Andy Millis, Jean-Marc Triscon, Ralph Place, and Johan Mahat for putting together this meeting, these very hard times and very difficult times, and doing this very nice job of getting this meeting online. And this will be the optical conductivity lecture, de l'École de Physique des Houches 2020. And when Mark contacted me, he asked me to give the lecture on confined electronic states. And I said, okay, very easy, no problem. I have lots of stuff. And then there was that small fine print at interfaces. And then it's much harder, okay, because optics needs a lot of material. It's a very good technique because it probes the bulk of materials. So it doesn't have problems that you have in ARPIS or STM, surface quality, which is very important. It doesn't look at the top layer. It looks at the bulk. But when you have interfaces, you have no bulk. So I put sometimes at interfaces, I'll show whatever can be done at interfaces, so lanthanum aluminate on strontium titanate, graphene, but I also show confined states in a more general approach. So let me start here. This is the essential outline of this lecture. We will start with a crash course in optical conductivity, and essentially try to build the perception of the optical conductivity from raw data. I'll show you data and what that data tells us. If you're naively just looking at the data, what can you infer from it if you know a little bit of the physics of the material? And only after looking at the data will I try to quantify the response, putting what actually we are seeing in physical terms. And there are three basic concepts that you should retain from this lecture in optical conductivity. One is the Drude model. The second is the F-sum rule. And the third is that we look at joint density of states. So these are the three important things that you should retain from the optical part of this lecture. Then I'll try to show whatever can be done, confinement in real space. So building up dimensions, I'll show what quantum dots, it's almost a curiosity, but it's a fun curiosity. So the zero-dimension quantum dots optical response. For 1D, I chose to show organic conductors. So this is confinement by the structure. It's not an artificial structure that you're building. It's just the essential structure of the material that conducts in one dimension, and it has interesting physics on it. And for 2D, I chose two examples. One is the lanthanum aluminate on strontium titanate, which is at the heart of this school. And the other material, you can look at it whatever you want. I look at the graphene as interface-only material. It has nothing else. It only has the interface. And I'll try to discuss what's the effect of the confinement because of that interface, and what's the effect because of the strange band structure. And in a third portion of this talk, I will try to look at confinement in reciprocal space. So what happens when the states you have accessible are not just those plain large bands that you would have in condensed matter. Okay, so let me start with this very brief guide to the optical conductivity. I want to make a warning here because of the habits we get. I'm going to use optical conductivity, optical spectroscopy, and infrared spectroscopy as interchangeable words. For me, they're all the same, so there's no distinction in what I'm saying. They're not exactly the same thing, but in the matter of this talk, if you hear one or the other, they are the same thing. You can look at infrared or optical spectroscopy as a particular case of light scattering. The purists say, no, infrared is no scattering at all. You're not scattering light. But you can look at it as a general case. And the general scattering case is you have a source that will emit a photon. That photon is characterized, of course, by electric field and magnetic fields at a certain frequency, and it has a wave vector. It has a momentum. You get inside this box. This box is whatever you have, your sample, your cryostat, your interferometer, your refraction grating, whatever you have to analyze that photon and make it interact with your material. Your sample is inside the box. And then you get something out, which is another photon, electric field, magnetic field, at a generic frequency and at a generic wave vector. The particularities of infrared spectroscopy is that, first, it's a momentum average technique. So the momentum of the outgoing photon is the same as the incoming photon. The change in the momentum is very small, so it's very close to zero. If you look at the literature, you will find quite often optical spectroscopy, infrared, and even Raman is stated as center of zone techniques or gamma point techniques. I don't like that description because it's reducing, and that's strictly true only for bosons at zero temperature where you have a minimum at the gamma point. Then it's strictly center of zone. For everybody else, what you're doing is any vertical transition that preserves momentum will be accessible by infrared if it's a charged transition. Okay, so you average, you don't have momentum selectivity like you have in ARPIS, like you have in RICS, but you do access more than the center of the zone. You just average amongst it all. The second aspect, it is that the frequency out is the same of the frequency in. Okay, so it's elastic light scattering, as opposed, for instance, to Raman spectroscopy, where you excite at a certain color and you look, the response shifted in frequency, shifted in energy to that color. That's inelastic. The third point is a gift and the curse. Okay, infrared or optical spectroscopy is a broadband white light spectroscopy, meaning that you have access in a very large range, in a very large spectral range, optimally from 0 to infinity frequency. Of course, we cannot do all of that, but that would be the ideal case. That's the gift, because you can look at interactions between different excitations, but that's also a curse, because it's not a possibility. I will show you later. In many cases, it's a requirement that you have to measure in a very broad band to get good data. And the final characteristic here is that the electrical susceptibility of materials is much bigger than the magnetic susceptibility. So whenever light interacts with a material, it will be an interaction between the electric field of light with charged excitations in that material. You could have an interaction between the magnetic field and magnetic excitations. It's so small that if there is any charge hanging around at that energy range, it will mask the magnetic response. Little word on what we measure. Essentially, most of what I'll show you here is either in reflectivity or transmission geometry. Very easy thing. You have a slab of a material, you send light in, you measure what comes back, or you measure what goes through. So transmission is very good because it's very sensitive to very small signals. You remember from your optics courses, absorption goes exponentially with sample thickness. So if you have a very tiny signal, but a thick enough sample, you can amplify that signal by going through the sample. Transmission is also very easy to align. You have just to go in a straight line to get your detector. But of course, the sample has to be transparent, and you have only information access to those transparent regions. Reflectivity is less sensitive to very tiny signals, but it has no limitations in the spectral range. It has no limitations on bandwidth. So it's a very useful technique. It requires more alignment, but most of what we do is using reflectivity. So let me get to data. I promised I would do infrared spectroscopy or optical conductivity data. This is one of the most simple spectra you can find. It's silicon, undoped silicon. It's an undoped 300 microns, 0.3 millimeter silicon slab. A lot of information on this picture, even if it's very simple. First one is this units here, wave numbers. These are the typical units that you're going to see in a paper talking about optical conductivity or infrared spectroscopy. It's just the inverse of the wavelength. And the reason for this is that Fourier transform spectrometers get out this unit in a very natural way. Okay? You measure a distance, and the Fourier transform of it is the inverse of the distance. So this is the natural unit for it. It's a very useful unit in the sense that it's linear in energy. So you can convert it directly to energy in electron volts, remembering that 8,000 wave numbers is 1 eV. It's also, you can start seeing now papers showing terahertz frequency. It's also linear in frequency. And it's the reciprocal of the historical wavelength units. Wavelength were the natural units for dispersive spectrometers. So in this lecture, I will essentially show you data in wave numbers or in electron volts. I think most of it from now on will be in one of these two. Let's get back to silicon. So silicon, forget this small thing here, okay? Pretend it doesn't exist. It's really tiny. If it doesn't exist, silicon would be a flat transmission, constant, all the way to a threshold here, where it drops sharply, and then it transmits nothing. So what you're looking here, knowing that silicon is a semiconductor, is essentially the band gap absorption. The photon energy below this threshold is not enough to excite an electron from the valence band to the conduction band. As soon as it goes above the gap, that energy, you can excite vertically electrons from one to the other, and then your transmission goes to zero. The photon gets absorbed by the excitation, re-emitted at a random direction, so the random direction generally is not towards your detector, so it just drops to zero. So with a very simple measurement, you just got the band gap of a semiconductor. This thing here that I said ignore it, this is a second order harmonic effect phonon of silicon. Silicon is a homopolar material, meaning that silicon atoms, they have the same charge. They don't have a positive silicon and a negative silicon. So there's no dipole momentum between two ions. Infrared, I mentioned, couples to charges. So you have no coupling between the photon and a phonon in silicon. There's almost nothing. So I'll ask you to remember one thing. There is a small drop here, maybe 10% of transmission for a 300 microns thick sample. Let me complicate this spectrum just a little bit. Oh, you should know I measured this especially for this school, okay? I'll look now at mercury cadmium telluride. Another semiconductor. Pay attention, this is a log scale. The previous one was a linear, this is a logarithmic scale. It tends to maximize the low energies. If I forget everything below 100 millivolts, you have two temperatures here, 77 and 300 K. Below 100 millivolts, it's essentially the same thing as silicon, that flat, reasonably high transmission with a sharp drop at the band gap edge. But now that small, tiny phonon of silicon becomes this thing here in mercury cadmium telluride. In this material, which is thinner, it's a 10 micron thick MCT, so mercury cadmium film, on CTTE substrate without the mercury. And the total thickness is about 2/3 of the previous sample. It's not a 10% drop. You go all the way to zero and you see nothing anymore. So that's the problem of the transmission. It goes very quickly to zero, and then you don't know the size of the zero. Is it a big zero? Is it a small zero? I cannot quantify. But because here you have positive ions in mercury and cadmium and negative tellurium, and they will have a dipole momentum that will couple to the electric field of light, and then the absorption is very high. That's not all. Mercury cadmium telluride, I'm showing two temperatures, not just to brag that I can measure at low temperature. It's even that low. But if you look at the very far infrared, at the terahertz region, that's now it's trendy to call, the room temperature red line is below the liquid nitrogen blue line. This means that you have some more absorption at room temperature than at low temperatures. And this comes from the semiconducting nature of mercury cadmium telluride. You have a thermal activation of charge carriers. Temperature will populate a little bit the conduction band, so you have really poor metal there, but those free electrons will absorb light. And then when you cool down, they collapse back to the valence band, and you don't see that absorption anymore. So this figure is telling you, okay, I see the gap, I see polar vibrations, I see phonons, and I also see free carriers. But transmission is not very reliable when the sample becomes opaque. So generally, we look at reflectivity. So remember, I have high transmission, and I have a peak down, a drop, when I have an excitation. Reflectivity is different. I will have, now instead of drops, when I see an excitation, I'll see peaks up. So this is the reflectivity of iron oxide. Antoine Georges showed this on his talk on Monday, if I remember well. He was telling about transition metal oxides and was telling about rust. This is one of the forms of rust, Fe2O3. And in this iron oxide, you see a few interesting things. First, you see those phonon vibrations that made the transmission of MCT drop to zero. Here, they appear as up peaks. So you have 4 of them. You have 1 here, 2, then a 3rd peak here, and a 4th one here. These are predicted by group theory. There's nothing new there. These are phonons of iron oxide. But now you can look at the spectrum and see, oh, I know how to look at the transmission. I know how to look at the reflectivity. And there is something else here, close to 2 electron volts. And this is an interband transition that Antoine calculated for other materials, for vanadium oxide, essentially. And this is what gives the red color of rust. Okay, this is very close to a red light. So this gives the red color of rust. Very well. So let me get to another example. So now you're experts in looking at reflectivity of insulating materials. This is reflectivity logarithmic scale as a function of frequency for YBCO. This is a high temperature superconductor. It's not superconducting in this data. YBCO is an oxygen pump. You can have from 6 to 7 oxygen atoms per unit formula. And when it's close to 6 atoms per unit formula, it's rather insulating, and it's also anisotropic. It's in this configuration, it's tetragonal. You have a basal plane that's more conducting than the C direction. So the data I'm showing, that I'm showing here to you is the C direction at the very close to O6 material. You know what this means. These are peaks up showing phonons, and there's not much else going on here. Now, the DC conductivity of this is 10 to minus 6 inverse ohm centimeters. If I start putting oxygen here and look at the basal conducting plane, I'll get this YBCO7 reflectivity. And you see it's radically different. It's a 10,000 inverse ohm centimeters sample. And all those phonons were replaced by this very flat, very high reflectivity. Even if it's log scale, it makes things a little bit false, but it's very high reflectivity. You can still see a peak here and a peak there, which are remnants of phonons, but they are all gone away. This is the free electron response, the free carrier response, the mobile carrier response. So this, I intend to show that optical spectroscopy is an electrical transport measurement. Okay? Between a metal and an insulator, the distinction is obvious. Let me try to quantify these things a little bit. So this is probably my most formal transparency or slide. If I start from Maxwell equations in matter and I assume a plane wave, everybody has done this exercise once. Put vacuum conditions, meaning no net density of charge, no current density. Combine these equations and you will find the wave equation for electromagnetic propagation. And this is a wave for the electric field wave propagating at speed c, the speed of light, which is the product of the vacuum permittivity and permissivity. Now I'll do the same, and I'll do this inside a material, for my case a conducting material. So the only difference I do is to enter now a current density. So the current density is proportional to the electric field through this coefficient, through the conductivity. And because this is frequency dependent, the conductivity is also frequency dependent. So at zero frequency, this is the conductivity inverse of resistivity of the material. At finite frequencies, we call it optical conductivity. But it's the same thing. The DC conductivity is just the zero frequency limit of the optical conductivity. You do the same exercise and you find this wave equation. It's essentially the same thing as the above one. With this factor here, renormalizing the speed of light. So the speed of light is renormalized by the square root of this. And this is essentially the definition of refraction index. So this is the relation between the optical conductivity and the refraction index, which square is also called the dielectric function. This small square bracket term here is essentially the heart of optical spectroscopy. You have the three most important optical functions that you can imagine and the relation between themselves here. So the dielectric function, the refraction index, and the optical conductivity, they all measure the same thing. They all have the same information presented in a different way. So you have to choose which one to use according to what message you want to give. But the information is present in all of them. And also remember, these are complex quantities. Okay, they have a real and imaginary part. So how can I measure it? I'll give you two examples before getting to the reflectivity, the way to measure it is one way, very common way, is to use ellipsometry. And I'll show some ellipsometry data later. So you have light with a well-defined polarized light going to the sample. It gets reflected, generally close to grazing incidence. And you have an analyzer at the output, and you measure this reflected light as a function of the analyzer angle. So you measure all the polarizations at each angle. And then you draw an ellipsis. This ellipsis will have two axes. From the dimensions of those two axes, you can deduce, you have two measurements, you can deduce real and imaginary part of the complex function. It's a very powerful technique. It has two problems. Because it's grazing incidence, your effective sample size is very small. Okay? Even a large sample, when you look from the side, becomes small. And it's very difficult to do in the far infrared. It's not impossible, but it's difficult. Only very few prototypes exist in the far infrared, generally in synchrotron facilities to get more brightness of light. Another very fashionable technique is times domain terahertz, where you have an ultra-fast laser, generally a TISAF laser. You have a pulse of this laser that's split into two. One side of the pulse excites a terahertz emitter, a nonlinear crystal that will emit terahertz light, and the other half of the pulse will excite the detector, will trigger the detector. This terahertz goes to your sample, interacts with your material, and is sent to the detector. Again, you have two pieces of information because the same laser light is exciting sample and detector. You can measure the delay in time between the excitation and the detection. You can measure the amplitude. You have two quantities. There you have, you can get the optical function. Here it has a few problems. The first one, it's limited to the terahertz, to the very far infrared. And the second, it's a complex geometry. It's not a measurement that just drop your sample in and take the data. You need large samples. Generally, transmission is better than the reflectivity. It's more complicated. The jack of all trades here is reflectivity. It has not many limitations. It measures everything, but these are Snell-Descartes equations, relation between the refraction index and the reflectivity, near normal incidence. And the reflectivity is one single real valued measurement. So to get the complex functions, you have to get something. I'm not going to make a lecture on this, but the name of the something you do is Kramers-Kronig transformations. So Kramers-Kronig, in a nutshell, just to give you the origins, is Cauchy theorem that will relate real and imaginary parts of a complex analytical function. Then you go that only to integration in the full real axis from -infinity to +infinity. Using the residue theorem, you will find what's called Hilbert transforms. Then you use causality. Causality is telling you that your measurement can only be done after you made an excitation on the sample. Okay, things have to happen in a certain order. This will allow you to integrate only at positive frequencies, and then it's what's called Kramers-Kronig transformations. You can look in a book, that's what it gives. Does it work? So this is the reflectivity of a nictide superconductor, barium, iron, cobalt arsenide. The solid line here is the optical conductivity obtained from Kramers-Kronig. The dots are on the very same sample, the ellipsometry measurement. So we know what we do. We can get a very good result using this technique. The advantage it is broadband, but here is the curse. It needs the broadband because of Kramers-Kronig. You have to integrate at all frequencies. And you need to guess a little bit because you cannot measure from 0 to infinity, so you have to figure out outside your measurement range, what does it give? So let me get now to the metallic response. Okay. The easiest model created by Paul Drude in year 1900, assumes that you have a free electron gas, no screening at all. You don't have electron-electron interactions, you don't have electron-phonon interactions, you only have elastic collisions. So electrons bang around, and you have a typical lifetime, typical scattering rate between two collisions. So this scattering rate is this 1 over tau, the lifetime is tau, and you have the density of electrons that will give you sigma naught. Everybody has seen in his introduction course for solid state, has seen this equation here, sigma naught, given by the density of electrons and their lifetimes. You can extend this very easily to finite frequencies, and then you have the optical conductivity, which of course at 0 frequency reduces to sigma naught. You can also write this in terms of dielectric function. Remember, they are two related. The imaginary part of one is the real part of the other. And this is useful to use the concept of plasma frequency, very close to sigma naught. There is a tau difference here between the two values. The reflectivity of a Drude model is this picture here. For the sake of this lecture, forget epsilon infinity. Assume it's just 1. Okay, I'm not going to discuss it. The reflectivity is 1 all the way to this plasma frequency that we also call plasma edge, and then is 0 or very low afterwards. So this is what telling you the meaning of the plasma frequency. It's a longitudinal electronic wave that can follow the frequency of the light. Is being excited by the electric field of light up to a certain frequency. Then the frequency is too high, that longitudinal wave cannot follow it anymore. That frequency is the plasma frequency. This is also what you see every morning when you comb your hair, when you brush your teeth, when you shave yourselves. You're looking at the mirror. So what you're actually looking is at the Drude model. And I'll get back to this. If you look at the optical conductivity, I plotted here this equation. This is not just a cartoon, it's a plot of that. It's a Lorentzian centered at 0 frequency. Its maximum is sigma naught. Its width at half maximum is the scattering rate. I'm plotting this peak here for comparison. This is what's called generic bound charge excitation. So if you're in a party, people are talking about optical conductivity, you don't want to feel set aside. You can always say this, hey, look, optical conductivity, I know very well. If you have a peak at 0 frequency, it's a free carrier. If you have a peak at finite frequency, it's a bound charge carrier. Everybody will think you're really smart in optical conductivity. That's essentially the case in almost every case. There are exceptions, and I'll show you one. But if you say that, you look smart. People think you know about optical conductivity. Does it work? The Drude model, is it considering nothing, it should not work, yet it's very good. So this is the reflectivity. I apologize, the transparency here is in French, so I think you can find out what reflectivité et fréquence mean. But you have the reflectivity of aluminum, gold, and silver. 3 very common metals. Gold less common in my pocket than the other 2. But essentially we'll have that reflectivity very high up to a certain edge. So silver follows that very well. Gold follows it pretty well, but then there are interband transitions here that will kick in. And aluminum, there is one interband transition, but it's also very good. So this aluminum here is what you see every morning in your mirror. It's a Drude Plasmon. Your image is given back to you by the Drude model. And for instance, the gold plasma edge, and I want to use the word plasma edge here because it's more accurate, is around 2 electron volts if you make the conversion, giving that gold color or yellow color if you're less sophisticated to gold. You can also tweak that very well. This is indium antimonide, the reflectivity, and several samples. This is n-doped, if I remember well. So it's electron doped, negatively doped. And it's moving up simply because you're injecting more electrons through doping. So you see perfect agreement between the dots, the measurement, and the Drude model. How about the conductivity? And this will give me a bridge to the next point, is when Drude model doesn't work. So as an example, I took this Mayenite material. These are electrons in a cage. So you have a cage, this very filled optical chemical formula here, very many atoms. So you have cages like this, and in one unit cell you have 12 of these cages making this thing, and one every other 3 cages can trap an electron. So you can have 4 electrons per unit cell. And you can release them or capture them back by using UV radiation going through a metal insulator transition. This is the reflectivity as a function of energy for a series of samples. Very low reflectivity is the insulating, and then you see that profile increasing for the metallic samples. You know this picture very well already. You have the peaks up, which are phonons. You fill them, you get the metallic response until the phonons are almost gone. Chromoscrotic on this, optical conductivity. So I start with a very insulating sample. Pictures of the samples are here from white transparent to dark black sample, very absorbing. The conductivity is essentially 0. The dots here, this color here is wrong, okay? But the dots are the DC conductivity measured by transport for these 3 samples here. So it's essentially 0 conductivity for the very insulating samples. The blue sample is a Drude, and I'll add the word like here. It's a Drude-like peak, and I'll get back to this. And between the two, you see the electrons filling the response and getting that Drude peak. With an interesting thing, there is sort of a finite frequency centered bump here in the red and the black curves. So before the electron gets free, it sort of gets locally delocalized. You get that bound carrier, but not that much bound. I mentioned Drude-like peak here because if I go back to my cartoon, you see that the Drude model goes to 0 very quickly. Well, here it doesn't, okay? And this will be my next slide. It doesn't because Drude model is not enough to describe this. This is the hallmark and the signature of electronic interactions or electronic correlations. So how we describe it, there are many ways to do that, but Drude model proposed this. Phil Allen in '71 proposed to extend that Drude model by adding, I can rewrite the model instead of sigma naught by using the plasma frequency so that the scattering rate gets here. Phil Allen put a frequency dependency in the scattering rate, and because of causality, because of Chromoscrotic, you need to put a frequency dependent term here. That's a mass renormalization. Now you have to do 2 things here. You can do 2 things. Either you're a theorist and you create a model for a frequency dependent scattering rate and try to see what it gives in a Drude model, or you are an experimentalist. What you do is take this measurement, invert the equation, and look what the scattering rate for that material is, what the mass for that material is. For example, let me take a strong correlated material, a bad metal here. This is BISCO, bismuth, strontium, calcium, copper oxide. It's a superconductor. Again, not at a superconducting temperature. The conductivity is the red line. The Drude model is the blue dashed line. And to describe this conductivity, I have to add a lot of spectral weight, a lot of stuff at finite frequencies. Okay? And these are not bound carriers here. They are truly the behavior of the material. So this is telling us that BISCO is not a perfect Drude model material. If I invert this optical conductivity to look at the scattering rate, I get this linear behavior here. Okay, so it's telling me for a Drude term, the scattering rate is a constant. Well, for this material, it depends linearly on the frequency. And if you read a paper on these materials and you see non-Fermi liquid, they are referring in part to this linear frequency dependency here. For Fermi liquid, this is an example of chromium. It should be a quadratic dependence. So this is still a debatable area in high TC superconductors. You can also get correlation effects in the effective mass. So the effective mass of a Drude model is 1, or the effective mass of the electron. Here, it's something different. You have interband transitions that will have a 0 crossing of the mass, so forget this. It will have the band mass that's here, and then correlations and bosonic interactions will bring it up to a larger value. So with this, you can make an analysis of the Drude model. If there is one message to retain from this optical conductivity, this is it, the F-sum rule. It's the conservation law. So I have been repeating continuously that we're measuring charge carriers. We're measuring charge carriers. Oh, it's a charge excitation, so on. I don't know if I told you, optical spectroscopy is measuring the charges in the material. So if you integrate the optical conductivity from 0 to infinity, you will get a constant, the electron charge, times the number of electrons divided by the electronic mass, plus the number of protons divided by the proton mass. Rigorously, this is what's going to give you. This term is 2,000 times smaller than this one, so you just drop it. Essentially, you get, because of the mass, of course, and essentially you get the number of electrons in your material. All of the electrons, not conduction electrons, all of them, okay, if you're integrating from 0 to infinity. So this number cannot change for a material. If physics is right, this is a fantastic law. This number cannot change. What does it mean? That if I have a phase transition, that if I change temperature, if I change pressure, if I change any external parameter, this number should not change. Example for this phosphorus tungsten bronze here. So this has a charge density wave transition. At higher temperatures above 140 K, it has this Drude-like, again, you gotta get accustomed to the like after the Drude. So it's a Drude-like profile decreasing for the conducting side. When you go through the transition, you open a charge density gap, the conductivity drops, and so does the low frequency optical conductivity. You lose a spectral weight here. The sum rule is telling this spectral weight cannot disappear. It has to go somewhere. It goes above the gap. So you see spectral weight transfer, and this is a very useful tool in infrared. Look at spectral weight transfer. Where the excitations were, where they have gone. And the area that you lose here is exactly the area that you gain here. Nothing's lost, nothing's gained, conservation of total charge. You might see papers saying sum rule violation. If you read the paper, you see it's not really violating the sum rule. It's just transfer is going to places we didn't expect. So sum rule should always be fulfilled, and it's a very good check of your data. Your data respects sum rule, it's probably good. My final transparency on the optical properties before I go to data on confined states for the second half of this lecture is the joint density of states. So you're going to see here, this is what I'm going to discuss. You're going to see this CV index here. This comes from conduction and valence. A lot of the theory for this was developed for semiconducting materials, so they use this naming. Other people will put OP for optics, the density of states measured by optics, and other people will just put nothing, and you just deduce from the context. So what's the joint density of states? Keeping track with history, I'll use the semiconducting approach. So you have the valence band, you have the conduction band. This one is filled, this one is empty in my case. You send a photon of energy h bar omega. It will pick an electron here and make a vertical transition. Remember, delta K equals 0, vertical transitions from here to there. So to see something in optics, you have to take into account the density of states of this band and the density of states of this band, hence the name joint density of states. You also have to take into account the occupation probability and the matrix element. So in this equation here, I'm assuming this is fully occupied. I'm not taking the Fermi functions here. I'm assuming that the matrix element is independent of K. First good approximation, so I'm just taking it out of the integral and out of my equation. And the density of states, the joint density of states, is just the sum of delta functions, okay, of these transitions between conduction, valence band, and h bar omega, the energy of the photon. It's exactly the same thing you do to calculate a density of state in a band. The only difference is that you only have one band, not the two. And if you do the same manipulation, the same mathematical manipulation, you can calculate this integral in surfaces of constant energy. And when you do that, you have what you have also for a single band, the inverse of the K gradient of the band. But here you have the inverse of the K gradient of the band differences. This is the optical analog of flat bands. So people love flat bands because it gives very high density of states. Infrared and optics also like flat bands, but not that much, because having a lot of density of states doesn't give me much infrared signal. But the equivalent of flat bands in optics is parallel bands, is when this gradient goes to 0. So you have parallel bands, you have the difference that's going to 0. You have a large density of states, joint density of states. Example here, germanium. So this is the band structure of germanium. If you look at it, you will see two regions, the yellow region here and the red region here, where you have sort of parallelish bands. Okay, so the signature of this yellow band in the imaginary part of the dielectric function. So this is close to the real part of the optical conductivity as a function of energy. That's the contribution of that parallel region, those two transitions between those two parallel bands, the red one between those parallel bands here. As an observation, look that the gap is here. The germanium gap is here. You can see it here in the data, okay? But it's really tiny. There are no parallel bands here. So you detect the gap, of course, but the big signals come from the parallel bands. So joint density of states. So that's it for the optics. I didn't talk much about phonons. I did talk much about magnons. We can see many other things. But for the conducting media, that's what I wanted to show you. And try to remember these three things here for the rest of this lecture. We are measuring charge carriers, so insulating and metallic behaviors, localized carriers, localized charges. A phonon is a localized charge, it's a dipole momentum. And free carriers behave differently. Sum rule is a very powerful and important tool to check the data and to look at spectral weight analysis. And what we look at, and this is particularly important in graphene, is the joint density of states. Okay. So let me have a sip of water. And let me move to real space confinement. So it will be close to the second half of this lecture. What I'm calling here confinement in real space, either because the material has that property intrinsically, either because we act upon it so that electrons are not as happy as they could be in 3D, or maybe they're happier, depending on how you look at it. I'll start with the 0 dimension. So this is a very good playground for semiconducting physics. You take a semiconductor, you can create a heterostructure, you create a quantum well. So you're confining one dimension, electrons can move in 2 dimensions. So this is a big chunk of semiconducting physics. Now, not happy with that, you can confine a second dimension and leave electrons to move in 1 dimension. So you have the quantum wires. For instance, carbon nanotubes are good quantum wires. But you're still not happy. I can confine more, so you confine all 3 dimensions. You have 0-dimensional physics. Okay, so you have the quantum dots. And the interesting thing, this is an example of the optics of quantum dots that you can see. I'll get back to this. How confined is confinement? So to get an idea of what sizes you need here, you can look at the energy of confinement. So let's say that I have a particle that will have some size that I'm calling delta x. By Heisenberg uncertainty principle, I can calculate delta p, the momentum spread for that particle, and then calculate the confinement energy. Okay, I can put back delta x here, so I replace delta p by delta x over h bar, and I can compare that confinement energy with temperature. And so that the physics of the material is really confined states physics at a given temperature, this inequality here must hold. At room temperature for a semiconductor of 0.1 electronic mass or effective mass, you will find that typically you have a few nanometers of size required to have confinement states. These are CDSC nanoparticles from 2 to 6 nanometers. Funny thing, they are the same material. They are diluted in a solution here, those nanoparticles, but they are the very same material. You're only changing the size. Okay, these are big nanoparticles, 6 nanometers. These are small nanoparticles. You go from red to blue. You can cover the whole rainbow spectrum. just by changing the size, not the composition. How can we look this very crudely? So if you are in 3D, you have a band structure for a free electron, a density of states, which is a square root. If you go to 1D, you have delta functions. If you have a semiconductor, you also have a gap here, so you shift everybody up here. So what's happening here? In a very crude vision, you can think of CDSC as a semiconductor with an infrared gap or a red gap. And that's bulk, so that's the color it will emit. So you shine it with UV light and re-emits the photon. Now, when you shrink the particle, you start going back to the atomic physics. So you're going from the collective solid state mode to the atomic mode, where the difference between levels is in the UV. So by shrinking the particle, you're moving the gap up and you're splitting the levels, you can get any color. And you can really get any color if you play with composition and with size. So these are not nano dots, these are nanocubes of cesium, lead, something being chloride, bromide, or iodine. You have small cubes confined in real space. Here you have a picture of many of those cubes, nicely arranged. And I think you have not seen this yet. This is a perovskite, right? I think every talk up to now mentioned perovskites. Here they are. Perovskites are important here too. And by changing the composition and the size, you can very finely tune the photoluminescence of those materials, okay? What I mentioned about going from bulk to atomic physics is summarized in this picture. So for bromide, cesium, lead, bromide, you have the bulk gap, which is about 2 eV. And when you decrease the size, that gap is increasing and going to the UV, okay? This here is just a curiosity. This is a chart that people doing flat screens use for color. The dots here are all the colors that you can obtain from this nano dots, the nano cubes here. Quantum dots are very useful for flat screens, especially if you like, as Marc-Gabet said, my other profession as a professional soccer player, if you would like to watch football and the TV, because your TV you have at home, it's very good to produce red, it's very good to produce blue. It doesn't have a very good green. The light sources we have for green are not good. If you use a quantum dot, they are wonderful. So if you look at soccer in a quantum dot TV, it's a perfect grass color that you're going to see. I think Samsung is selling those QLED flat screens now. Final word on this, you're not restricted to the visible light. You can tweak nanodots from all the way to the mid-infrared. So this is mercury telluride, another very useful material. They can emit light in the infrared, and you can go all the way to the terahertz. So you see this absorption coefficient you can find here at frequencies of a few terahertz, very long wavelengths. So this is a wonderful playground, and with optics you can characterize this very nicely. Let me add one dimension to my problem. So the one dimension that I add is an organic conductor. So I just put the name here to see if I could say it, Tetramethyltetraselenofulvalene 2, X. X is easy, it's phosphorus, arsenic, antimonium, or tantalum fluoride, or chlorum and rhenium oxide. Okay, so this is an organic conductor called TMT-SF. There's also a version TMT-TF. SF, if I remember well, is selenium. TF is sulfur, in that long thing. And the structure of this are long one-dimensional chains. So these chains are conducting, and you have an almost 1D conductor. So here I didn't shrink the material as in quantum dots to confine the states. I use a property of a one-dimensional conduction to get the confinement in 1D. And this is an interesting problem because the one-dimensional conductors is what's called the Tomonaga-Luttinger liquid physics. Very crude experimentalist explanation of it. Suppose you have a one-dimensional chain, antiferromagnetic aligned. You put a hole there, you remove an electron. That electron can move around. And when it moves around after a while, you can reach this situation. You just make it jump here, 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 and make everybody else move. where you have a region where you have an empty space, you have a hole, so you have a charge, but you have no spin. You have a region here where there's a spin hanging around, but there's no charge, net charge associated to it. So you split the spin and the charge, you create a spin-on and a hold-on. And a funny thing here too, there's no more individual excitations. There's no single particle excitations. Every individual motion becomes a collective motion. This electron here, to move around, it has to push everybody else. Okay, when it goes here, it makes everybody else move with it. So every mode becomes collective. And you have a very nice phase diagram studied in Orsay very well. And you have the original paper here and a very nice review by Denis Jérôme. Optics of this thing, it's very interesting. It's much more interesting than this figure is telling you, because the authors here, they chose to plot this in a log scale, and the log scale is lying a little bit about what you want to see. So you have in blue here a Drude-like peak, and then you have a finite frequency peak here when you measure the optical conductivity along those chains. Because of the log scale, okay, if you put it back in linear, the Drude would be from 0 to, say, 10 inverse centimeters, 10 wave numbers, 0 to 10. This finite frequency peak here would be, say, from 50 to 1,000. Okay, so this is much bigger than this in area. There's much more things here than here. You can see this by looking at the spectral weight. So if you integrate the optical conductivity of this thing here, another misleading log scale here, the total spectral weight is this. The spectral weight of the Drude peak is this. Is essentially 1% of the total spectral weight. Why is that funny? Well, that's funny because the total spectral weight is required to account for the transport charge density. Okay, so the transport charge density, the charge density calculated from transport, is not coming from the Drude peak, it's coming from both peaks. Okay? And mostly from this one. What can we analyze from this? If you take that data and you collapse it, two things: you take the position of this peak and you take the height of this peak, and you normalize that curve for these three different materials: the phosphorus, the arsenic, and the chloride oxide. With those two conditions, frequency of the peak, height of the peak, all the three curves fall in the same one. Okay, and I will not go into the details here. Read this paper. In the Tomonaga-Luttinger liquid, you can show that the finite frequency peak is the gap due to the Mott transition. It's the Mott insulating gap. And in this liquid, you predict that this behavior here of the optical conductivity will be a power law. You don't know exactly which exponent, but it is a power law. And here it's measured to be 1.3. Okay. In this material, the Drude peak should not exist. It's a remnant of a Fermi liquid behavior because of interchain coupling. So we have seen 0 dimension, we have seen 1 dimension. Let's take a look at 2 dimensions with lanthanum aluminate and strontium titanate heterostructures. I think there is going to be a talk more specific about this, so I'm not going to enter in the physics of this. I think the first observation was this one. Here, I think it's the first observation of superconductivity in this material. Essentially, you take strontium titanate, which is a 3 eV band gap insulator, reasonably large band gap insulator. You put lanthanum aluminate, even larger band gap insulator. You put one on top of the other, the interface becomes a metal. The interface becomes a conductor. Okay? There are many reasons, there are many discussions. You have the problem of building up an electric field. Check for the talk on this later in this school. But what is funny here is that you can control the conduction properties of this material. So by applying a gate field here, an electric field, you can go in resistivity as a function of temperature, millikelvin. Recently, we wrote a report for activity report for our lab, and there are people working with this in our lab, and they put transition temperature superconductor at the millikelvin. And there was a reporter that quoted superconducting transitions at megakelvins. He put an uppercase M here. So I don't know how's that going to end. I think we're going to get a call sometime from somebody looking for this megakelvin high TC superconductor. But anyway, you have an insulator. If you apply a bias voltage on one side, and you can go metallic, even at 0 voltage is metallic, and eventually superconducting. So it's fascinating playground for this physics, even though the temperature is quite low. What is even funnier is that the interesting thing is not the lanthanum aluminate, it's the strontium titanate, because if you put lanthanum titanate on top of strontium titanate, you'll find the same thing. Okay, you find the same insulator to metal to semiconductor to superconductor behavior. Okay. There is one point that I wanted to stress here, 2 points. One, strontium titanate is the boss. He is giving the cards here. And the second one, it seems to have a 4-unit cell critical thickness for lanthanum aluminate, and this will be very important in optics to validate the data. Below that thickness, there's no 2D electron gas, at least in some of the samples. This is the optics of lanthanum aluminate on strontium titanate. So everything begins badly, okay? Bad beginnings, because this is the optical reflectivity of strontium titanate in the range, so reflectivity as a function of frequency, in the range where metallic physics of the heterostructure will be good. So remember, an insulator is low reflectivity, a metal is high reflectivity. So looking at the metal insulator transition here would be low reflectivity of high reflectivity of lanthanum aluminate. The problem is the strontium titanate is already almost 100%. These are polar, very polar phonons that give very high reflectivity here. So it's almost 100% at low temperatures already. So you cannot go above 100% reflectivity. So the problem, if you put lanthanum aluminate, you're going to increase this by nothing. That's why. And moreover, you would only put a few unit cells of lanthanum aluminate. So you have a very small increase, and you have not any material at all to look at. So it's a really hard measurement. It was done. It's a Christian Bernard group in Fribourg that used ellipsometry. It's a very adequate technique to look at this kind of very small signals. On 2 lanthanum aluminate on strontium titanate samples, 3 unit cells, 5 unit cells. And this is the 5 unit cell response. There are 2 curves, epsilon 1 and epsilon 2. Real and imaginary parts of the dielectric function, so imaginary and real parts of the optical conductivity within a factor of omega. If you look at these curves here, blue and green, strontium titanate and strontium titanate plus lanthanum aluminate, they are essentially the same, right? So you have to really zoom it out to see that there's a small difference. And the small difference is maybe 0.5%. So you need that accuracy in absolute values to say that you're seeing something. Really hard measurement. Do we believe it? And that's why the 3 unit cells is very important. Yes, we do. So this is the differential dielectric function, okay? Strontium titanate plus lanthanum aluminate minus strontium titanate. And let me look only at the 2 top panels. The 2 top panels is epsilon 2, the bottom panels is epsilon 1. So let me look at the conductivity. That's what's really mattering for me here. 5 unit cells of lanthanum aluminate, 3 unit cells. Here you should have the 2D electron gas. Here you should not. You see that the dots here are the differential data. The lines are Drude modeling of that data. Not perfect, but there is some free carriers here. They are not here. That's why you can believe that the data is good. So, and that's very impressive for them too. Makes everybody else jealous because it's really good data. And you do see the 2D electron gas. From this 5 unit cells, that's I'm going to concentrate here then, you can calculate the charge density and the mobility, compare it with transport. Mobility agrees very well. Open symbols are transport, closed symbols are optics. They agree very well. For the charge density, they agree very well all the way down to 100 Kelvin, and then there is a difference. We don't know where the difference comes from. There are a few possibilities. I'm listing them here. It could be that you have DC localization, like the one you see in the Luttigen liquid, for instance, that the Drude peak moves away from DC. You can have different depths in the probe that you're looking at, because you have a 2D electron gas. You could be looking at different penetration depths. Or you can also blame strontium titanate that has a structural phase transition at 110 Kelvin and might be doing either to the optics or to the transport measurement that we're not understanding. But okay, they track one each other pretty well. And you can also calculate the effective mass of the carriers. You find about 3 electronic masses, which is comparable to conducting strontium titanate, niobium doped strontium titanate. Can we analyze this more? Yes, we can. You can look at, here is this delta psi angle here is a direct ellipsometric measurement. So it's one of the angles between the outgoing polarization and the incoming polarization, one of the angles of the ellipses. I don't remember which one, either the large axis or the small axis, but it's not the important thing here. And you have in many materials what's called the Berman mode. It's when the dielectric function goes to 0. You have dips that appear, and we also call this longitudinal modes. Dielectric function going to 0 is a longitudinal mode. So they appear in the data. This is the strontium titanate phonon, and this is the plasmon, the 2D electron gas plasmon signature. So you see it in the data. The green dashed line is a fit of this data, considering that you have a square region inside strontium titanate of about 10 nanometers, which is conducting. So you have the green curve here, and it fits quite well, but not perfectly. You miss a little bit the high frequency here. So what the authors of this paper here did is they made a model where you red here is lanthanum aluminate, everything blue is strontium titanate. They made 4 slices, and they put different charge densities here. And they also imposed that the highest density is at the interface. So the electron gas is inside strontium titanate, highest density at the interface, and you model this in a stack of films optical model, and then you get the red curve. It's better than the green curve, okay? A little bit of wishful thinking, but it's better. And by doing that, you can model and you can profile the 2D electron gas within strontium titanate over what they find those 10 nanometers, and they can explain everything. So this is a very nice optical measurement of the profiling. And the conclusion of this is that this electronic gas here has a lot of similarities with niobium-doped strontium titanate. So let me move away from lanthanum aluminate and strontium titanate and look at another interface-only material, graphene. You only have a sheet of carbon. So it's only an interface, as I'm considering. You have probably seen this a million times. So you have in real space an hexagonal structure. In K space, it's also an hexagonal unit cell. You have 2 different points, K and K prime, where in the Brillouin zone corresponding to 2 different carbon atoms in the real space cell. And you have the symmetric band structure touching at those K and K prime points. So in pure graphene, the lower band is fully filled, the upper band is fully empty. Your Fermi surface would be these dots, okay? They only have dots. You don't really have a surface, you have dot surfaces at the K and K prime points. What is interesting is that close to this K and K prime points, you have linear dispersion. So you have those Dirac cones where you have linear density of states given by this. But optics, I mentioned it's not the density of states that matter, is the joint density of states. So if you calculate the optical conductivity, there will be a term here. You take a look. Oh, I didn't put a reference here, but it's in the next page. There is a reference. You can take a look at the deduction of this, but this will depend on a prefactor here of the optical conductivity. Fermi velocity, the joint density of states, and here it was calculated assuming tight binding of first neighbors. The Fermi distribution functions, if you go to 0 temperature, this is 1. The hopping integral, the lattice spacing will cancel out. What you're going to be left with is a constant optical conductivity equal to universal parameters. There's nothing from the lattice structure here, only E squared over H bar. Again, graphene is only a surface. There's not much material, really hard thing to measure, but it was measured. So this is Dmitry Basov's group data. I said that I want large samples and bulk. They measured this 50 micron samples and surface only, so interface only. So it's a really tough measurement. It was done in a microscope in a synchrotron facility in Berkeley, if I remember well. This is the real part, and this is the imaginary part of the optical conductivity of graphene. As a function, you have LEDs here for field-induced effects as a function of applied voltage. So at 0 applied voltage, it's hidden a little bit behind. It's the red and pink curve. The dashed line here is not because it's no data, it's just because they have a larger error bar here, but it's probably 10% error bar. So they didn't want to claim it was really flat. Here, there's plus or minus 10%, but it's still pretty flat. So this is the non-electrostatically doped graphene. It's exactly, you can look here, E squared over 2H. Pi E squared over 2H bar. So E squared over H. So it's that universal value, constant conductivity. When you apply an electric field, what you're going to do is, let's take this cone here. I'm applying a field here, pushing the Fermi energy down. So I have the field states are red. I pushed the energy down. Fermi energy here is here. And now I created a gap in my system. Not a real band structure gap, but an optical gap. Because remember the joint density of states, I need initial state, final state, I need density of state in both, but I need one of them to be occupied and the other free. So when I lower the Fermi energy, this transition where I have an electron here that I put there vertically is allowed, there exists, I don't want to use the word is allowed, but this one where there's nothing here to make the transition cannot be seen. There's nothing to make the transition. So you create a gap in the spectrum, not a gap in the band structure. And this is what we see here. This is a directly measurement of twice the Fermi level, okay? This shift in thing here. Remember the sum rule that I mentioned? Well, it states that the spectral weight I'm losing here when I'm applying the electric field should appear somewhere. And it does. We know where it should go. It should become the Drude peak because you now have many states to diffuse. And if you look at the imagine, but you cannot go very far in the infrared with such tiny samples. But you can look at the imaginary part, and then the Drude peak is much longer in the tail in the imaginary part. So you see that it's essentially 0 when you have a finite constant conductivity in the 0 field. And once you apply the field, you have this tail. So you're getting spectral weight from here and putting there. It's not quantitative, not yet. Wait for the next slide. But it's a very nice measurement. There are a few interesting points. This is the ratio between the Fermi level and the KF. So the Fermi level is the one measured by optics. KF is taken by the applied voltage. In a Dirac cone, it should be a constant. It should be the Fermi velocity. Okay, the energy is proportional to KF. What Dmitry and his collaborators saw is that it's not. It gets a deviation from that depending on the voltage you apply. And this, they speculated, can be due to many body interactions. There is an optical evidence for those many body interactions. The optical evidence is this one here. If you had truly a gap in the optical spectrum, you should have no transition at all until the Fermi level. Okay? Well, yet you have a residual conductivity, which is not vanishing. So this here, remember those residual conductivities that do not vanish in the strongly correlated materials. We say, oh, this is a many-body effect that will give a frequency dependence in the scattering rate. This could be this one here. So this is a clue pointing that there is many-body interactions that would give a scattering rate which is frequency dependent. The Drude. So these people here, a little bit later, made millimeter-sized graphene, really large flakes of graphene. And then you can measure better data in the infrared. It's still just a single layer, but it's very large surface. And when you look at the optical conductivity, the real part, as a function of electrostatic doping, so electrostatic gate function, you see that same thing. It's essentially no Drude peak at 0 voltage, and you build up a Drude peak as a function of frequency, very far infrared. So 150 wave numbers is 20 millivolts. Okay? In both the hole and electron doped sides, if you look at the mid-infrared, you're going to see that same, less nice data here than Dimitri's, but not as flat. But you see the residual conductivity, and this is a differential, so that's why it's negative. You see residual conductivity, and you see the Fermi level moving up. Okay. And this is very nice for two things, this data, because one, this picture here, you can compare in red the DC conductivity obtained from the Drude peak, in black the DC conductivity measured by DC methods. So they are right on the money. They have an asymmetry between electron holes that is disputable. I cannot discuss it here. Optics is not telling much about this. But you also have this other very nice picture here. And this is the sum rule. So the red dots is what's called the intraband transition. Fancy name for the Drude peak. Okay, so the transitions inside the conducting band. And this is the spectral weight, the integral over this Drude peak. The dark dots, the black dots or dark green, are the integral of the spectral weight lost at the Fermi energy. So it should be the negative. It's just minus that integral. It's the modulus. So you can see that whatever you're gaining in the Drude is coming from the gap edge, from the optical gap edge in both sides. It's a very nice verification of the sum rule that should be verified, as I stated a few times. But it's also a very nice verification of the data. I see this as validation of the quality of the data rather than the verification of the sum rule. So nice effects on graphene because they are confined, right? Well, not so sure. Because this is the universal conductance in graphite. So this is not graphene, or this is multi-layer graphene, if you want to call graphite that. So this is the bulk thing. This is the big thing, graphite. And what we have here is the conductance in units of that E square over H quantity, measured conductance as a function of temperature. So remember, it's flat down to 0 only at 0 Kelvin. Then you have the Fermi functions that will give this thing here. So, and I think this paper discusses that equation that I showed earlier. So you have that flat, close to 1 quantum of conductance value. This is the measurement. This is the calculation for this band structure calculated for graphite. And this is what is expected for graphene. So you're seeing graphene physics in graphite. Okay, you're seeing the conductivity here is plotted per plane, of course, not the bulk one. But the physics of the graphene sheet is reproduced in graphite. So here it's not only the confinement in real space that is important, but the confinement in K-space, limiting those electronic states only to the cones. And you see a few similarities in the band structure. You see a cone in graphite. You see more stuff. You can also explain these transitions here. Remember the flat band stuff? Well, here they are, the flat bands. Band 4, the transition number 4 is between this band and this band, which are parallel. So the flat band equivalent. Transition number 3 is this band and this band, which are also parallel. They are stronger than the other transitions. Okay. So this is the end of real space confinement. Let me move with this mixed state in graphite to reciprocal space confinement. And here the theorists are going to probably throw rotten tomatoes at me. I kept calling all this data up to now, oh, it's Dirac physics. And people say, no, your case is biophysics. Then I start saying biophysics, and other people, no, in your case it's Dirac physics. From the infrared's point of view, without magnetic field, it doesn't matter. What matters, you have cones. You have linear dispersions, not even cones, linear dispersions and band crossing, okay? But I tried to put here a summary, and I'll just skip this transparency of the difference between Weyl semimetals and Dirac semimetals. There are 3D analogs of graphene. There's this review by Peter Armitage, which is very good. There's this paper, I think it's on NMR, but I'm not really sure. But it makes a very nice summary of the various kinds of cones. So this would be the Dirac cones. This would be the Weyl semimetal. This is Dirac semimetal. There's inversion symmetry broken in Weyl. There's not in inversion or time reversal broken symmetry in Weyl, not in Dirac. You have Weyl nodes. Well, there are a few differences. For the optics, it's not really important. There is this very nice theoretical paper by Baxi and Virostek that made the optician life much easier. So what they took is, they took the generic case of two symmetrical bands touching at a point at the Fermi level, a non-interacting electronic system. And now they can solve this analytically if this band, and I don't know if I call it polynomial or power law, it's power law probably because it's just one term, if it has a power law dependence. And they find this optical conductivity here, which is very simple. It's omega, the frequency, to an exponent given by d. It's the system dimension, 1D, 2D, 3D, etc. 4D, I don't know. Maybe quasi-crystals could be 5D. But I don't think they are for optics. But anyway, 2D or 3D essentially is what's important for us here. And Z is the coefficient of the power law, the band dispersion. So if you have linear bands, you have Z equals 1. And in the 2D case, you will find a conductivity that is omega to the power of 0. So it's the constant that we have seen in graphene. In 3D, it's linear frequency dependence. The first paper, maybe, I'm not sure, but the first one that I saw is by Tom Timask and Chris Holmes, I think, on quasi-crystals. So these are icosahedral quasi-crystals. And what they said, this paper has the merit of raising awareness of the question, but it's not as strong as one could believe. So they said these quasi-crystals, they have a very strange optical conductivity that we do not see elsewhere. It's not a Drude-like optical conductivity, that would be that Lorentzian peak, right? It's not a flat with a band absorption. It's a linear optical conductivity. Okay, and there are those predictions of linear optical conductivity for Dirac linear dispersion physics in these materials. So they propose that these quasi-crystals, they have a few arguments to support that. They have band crossing, they expect, they don't have really good band calculations, but they expect band crossing without spin orbit coupling, but they maybe exist. They don't have inversion symmetry, so they maybe have two Weyl points. They say, let's say they do, and then we can interpret this as Dirac physics, and they calculate Fermi velocities which are compatible with measurements, and they say, hey, so the conclusion is linear dispersion in the optical conductivity is the hallmark of Dirac physics. I would take that with a grain of salt, and my last transparency will be that grain of salt. Dirac physics gives linear dispersion, the opposite's not true. But it has the merit of raising the awareness. There are other measurements, so here there are two. This absorption coefficient close to the optical conductivity in reasonably transparent samples. Mercury cadmium telluride, very useful material. I think there are two materials in nature, mercury cadmium telluride and strontium titanate, and probably the whole physics depends on them. So the mercury cadmium telluride has a linear optical absorption dependence in frequency. And this material, there's a lot of evidence that it has Dirac physics and linear dispersion at the Fermi level. ZET, was proposed, was measured as a linear dispersion material. And here is the example. So 2 examples of linear dispersion. This one has really Dirac physics on the back. This one, they propose it to have a Dirac physics because optics is linear. So there is some weight on that. Take that with a grain of salt. But they're pretty similar, right? You have more fancy Dirac physics that you can look. So this is CD3 AS2. This is Borisenko's ARPIS data on that material, and they find regions where you have those linear dispersions below the Fermi level. So you could call this a gapped Dirac physics. And if I remember well, this is Martin Dressel's team, but please check so that I don't make a faux pas here, quoting the wrong people. Measurements of optical conductivity. So the data is the black one. There is a Drude-like peak because there are other bands. Okay, there are not only those 2 cones. These are 3D materials. There is some residual conductivity here, more conventional. And then it goes up and almost linear. It's not exactly linear. It's omega to 1.65. The orange line is the optical conductivity calculation for this, and they would expect something proportional to this. So you have the omega square here, and then it kicks in something else here. So this is a nice effect of something unexpected that comes from those confined reciprocal space states. Another example here, last example on these cones, because I think I'm getting close to the end of this lecture. I'm fine on time, Mark. I mean, I have still 5 minutes or so.
Yeah,
okay.
Absolutely.
Great. So this is optical conductivity of tantalum arsenide. It's already we subtract a few things here that I'll not get into the detail, but the optical conductivity as a function of frequency. They have a Drude peak, the other bands, and then they have 2 linear regimes. This is another case. They say linearity in optical conductivity means Dirac physics, and not Dirac physics is giving linearity conductivity. But they make very compelling arguments, and they argue that this system has 12 Weyl points. Okay, so there's 12 Weyl points, and they would have 2 different situations. One, we would have cones. I should probably have lowered this right-hand side cone here. This is the Fermi level. They are at the same location. Okay, the Fermi level is not at different locations in the material. The Dirac cones here, they would have some at the Fermi level giving this linear behavior, and some where the Fermi level is in the upper cone giving this other linear behavior. And then they make a bunch of calculations, and they argue that this is signature of Dirac physics. The next step. So it's getting out from the Weyl cone or the Dirac physics to nodal lines. So nodal lines would be linear band dispersions that go through K-space. So you have 2 parallel bands like this, and they move in K-space. Not 2 parallel, sorry. 2 crossing linear bands, and they move in K-space. Okay. And there's this paper. There's a lot of good people in it. There is Tom Timusk, there is Andy Millis, there is Dmitry Basov, probably more people. There's a lot of authors too. And they have this case where you have not only the band crossing moving, but it also disperses in KZ, I think. And one example of this material would be niobium arsenide. The optical conductivity has a Drude peak, but has this higher frequency portion here with steps, with a maximum, with quite a few features that appear due to this linear dispersion that I will not enter in a lot of discussion, but that can be reproduced from theory. So this, you start to get into a regime where the optical conductivity is controlled by the different Fermi velocities that you have along and perpendicular to the nodal line. Okay, so it's a very interesting physics. a last example is barium nickel sulfide. This is a little bit of self-promotion. This is about to be published soon, I hope. This material, the band structure has two regions which have linear crossings between gamma and M points and between A and Z points. And the measurement of the optical conductivity is summarized here. The thick solid lines are 5K and 300K measurements, and you have this linear region here in the optical conductivity. What's interesting here is that you get that linear behavior from first principle. So if you just calculate this band structure and calculate the optical conductivity from it, you can reproduce those linear behaviors in the solid thin lines here, both temperatures. Now, this is the Brillouin zone. We can restrict the calculation of the optical conductivity to a certain region of the Brillouin zone. So we put a cylinder around those gamma M points. So there's a cylinder here. There are 4 times that cylinder. That's not drawn for clarity, but mostly to put stress on that point. And we see that most of the optical conductivity is coming from that restriction in the integration, in particular the linear portion of it. If you take it, so these are the dashed lines. And if you take the ratio of dashed lines, restricted Brillouin zone, to solid lines, full Brillouin zone integration, you have this side figure here. So between 70 and 90% of the conductivity is coming from those Dirac crossing, those linear dispersion regions. Okay. So you can get that from first principles. And I will finish probably with a word of caution, okay, because the optical conductivity was used and was mentioned to be the signature of Dirac bands of linear dispersion when you have that kind of bands in reciprocal space. The opposite's true. If you have Dirac cones, you will have linear portions in the optical conductivity, but it's not a two-way road. Okay, so I have 2 examples here. So this is gadolinium platinum bismuth. Data is in red, and band structure calculations is in black. So there is a problem in the amplitude, but that's very common. If you look at the band structure, there's maybe almost linear crossing here, but there's not really linear crossing. They're quite parabolic. They're more semi-metallic behavior that's giving this linear dispersion than linear bands. Another example is the cousin of that barium nickel sulfide that I just showed. It's the barium cobalt sulfide, which is insulating. And the data is the red portion here, also quite linear. Forget the blue line, it's not a matter here. But the blue line is small correlations calculation. The green and orange lines are strong correlation calculations. So we can also have linear dispersion, even though the amplitude is not exactly the same, but you can have linear dispersion from strong correlations. So remember, Dirac means linear, but linear doesn't mean Dirac. Okay, so that's all I had to tell you in this lecture. I will just grab my outline, cross out outline, and put summary to remember you what were the topics I covered. And thank you very much for staying with me this morning.
Thank you, Ricardo. Very nice. So during the meeting, there were a few questions.
Okay.
And I will invite those who ask questions to ask them live. So the first one was by Disha Aurora. So if you can turn on your mic and then ask the question.
Hi, so in the slide you mentioned that delta K is approximately 0. That is the momentum average technique.
Yes.
So how much close to 0 should it be? How to decide that?
Yes, that's where a blackboard helps. I cannot write in my computer. It comes from the dispersion relations of the photon. So the energy of a photon is proportional to its momentum. It's, I never remember. I'm an optician, I never remember. Energy is equals C, yeah, it's the speed of light times K, okay? So if you have the energy of the photon, you can calculate its, of the photon, you can calculate its momentum. So in optical region, if you just take that dispersion relation, the energy is C, omega equals C times K, not energy. The frequency is C times K. You can, for a given frequency, see what the value of K is. In practice, do the calculation, put the numbers in, and if you take a Brillouin zone with, for a crystal with a 5 angstrom lattice parameter, you're going to find that in optical frequencies, so meaning from the far infrared to the visible and UV even, your K of light is about 10 to minus 8 of the Brillouin zone boundary. Okay, so K, if you take pi over A as the limit, pi over A lattice parameter as the maximum K you need to cover the whole Brillouin zone, light would be about 10 to minus 4 to 10 to minus 8 of that. Okay. Does it answer your question?
Thank you.
Okay, but that's how you get it.
Okay, so the next question is by Xin Lu. So Xin, if you're able to, yeah. Go ahead.
Yeah, I think it has a microphone problem, right? So
okay, can you read the question?
Yeah, I can read the question. I
Ricardo?
just opened the chat window. So his question is, when one uses Kramers-Kronig relations to get the optical conductivity from reflectivity, how large the range of frequency we should choose in order to get a satisfying result? That answer changes with time. And did I put here? I don't remember if I did. Let me just go back to the Kramers, to the reflectivity, which is, where is it? Damn it. Okay, I'll just look for it. I'll just get it. There is a paper by David Tanner, and if I didn't put the reference here, you should, it will be in the notes of this lecture. No, I didn't put the reference here. So, okay, there is, if you ask me this question, say 5, 10 years ago, there was sort of a rule of thumb that if you do your job right, if you calculate the proper extensions, okay, so you measure in a certain frequency range, you should make sure that there's not much dispersion at the ends of your measurement, that there's not much change. And then you say, hey, my material is an insulating, I should go to 0 frequency this way because this is the way insulators go to 0 frequency. I should go to the 0 frequency this way because metals go this way. So it's a constant, or it's called Hagen-Rubens extrapolation. We know how to do that. But the biggest problem comes from high frequencies. How do I terminate my reflectivity that at infinity frequency should be 0? Nothing is reflected. Gamma rays just go through your matter. And there are several ways to do that extrapolation. All of them eventually end up with the free electron, which is 1 over omega 4. And 10 years ago, what you had to do was to grab your data, make sure that it fits all the conditions to have a good Kramers-Kronig, make the proper extrapolations. And then it was a little bit empirical. They would say, hey, we don't believe too much things that are in the last third of the data. So if I measured all the way to 1.5 eV, I don't believe things above 1 eV. I lose the last third. And on the other end, I lose about what I didn't measure. So if I measured all the way down to 1 millivolt, I also lose the first millivolt of the data. It's not horrible, but it's less accurate. There is this paper in the recent years by David Tanner, and it's a fantastic idea. Very simple. Above a certain energy, generally the low frequency extrapolation is not a problem. It's very easy. We are very good on that. The high frequency is up for grabs. And he wrote this paper, so the reference, it's Tanner, I think 2016 or 2015, Physical Review B. He said, above a certain energy, the solid material doesn't matter anymore. What matters are the ions and the atoms you put in them. And the scattering, the cross sections for X-ray scattering of every single ion useful for us, at least in the periodic table, has been measured and is well known. Okay, there are booklets for that as a function of energy above 10 eV. I think it's above 10 eV what we find. So from 10 eV to kilovolts, you know the scattering, the X-ray scattering section for every single atom in the periodic table. And he said, that's what matters to scatter photons. So if I know the atoms that I have in my material, if I know the density, I don't care how they are arranged. What matters, very high energy, is just the individual scattering. And I can calculate the reflectivity from those values. And he does, and it works wonderfully well. So I would say, and that's the picture that I showed comparing Kramers-Kronig to ellipsometry. I would say that today we have a very good accuracy, if you do your job well, to describe the data. Okay, the data here, it's measured all the way up to 45,000 wave numbers. It's my data. You see that, that a third rule is not really applied. I mean, if I go very close to 40,000 wave numbers, ellipsometry and Kramers-Kronig agree. So I'm very confident that if you do your work well, and if your material is not very badly behaved, you should use these new techniques. So in the lecture notes, there will be the reference to this paper. Okay. I think there was another question, right, Mark?
Yes, Pushpendra Gupta. So if you can come on and ask your question.
Yes, sir. Thank you, sir, for the nice lecture. And sir, my question is that as you told that for Lao thickness should be 4 unit cell for to getting the 2-dimensional electron gas in Lao STO structure.
Okay.
So, sir, what are the other parameter means which will needed to get 2-dimensional electron gas in this structure?
Well, the problem here is multifaceted. Okay. Ideally, you would like to measure only the 2D electronic gas, right? You wouldn't like to have the strontium titanate. You wouldn't have to like the lanthanum aluminate. So there is, first thing is, if you put 5 unit cells or 4 unit cells of lanthanum aluminate, you get the 2D electron gas. You don't want to put many more layers. In this paper here, they also show data with 50, I think, unit cells. And you don't want to put many more layers because then insulating lanthanum aluminate will also contribute to your optical response and will mask your effects. So first aspect, you would like to be as thin as possible to go through the lanthanum aluminate and get the good data on the 2D electron gas only. The second aspect is what I mentioned, the strontium titanate does not cooperate. You would like to have a strontium titanate with a very low reflectivity. But that means its dielectric function would also be very low, so we would not have any 2D electron gas. So this is a fundamental problem that you cannot overcome. So if you can overcome these two things, then there are two aspects. There is the thickness of the gas itself, okay? The optical thickness of the gas itself. And there is the surface that you can measure. So you would like to have as large a surface as possible because I mentioned infrared spectroscopy is an elastic scattering. You're measuring at the same frequency you're exciting. So when you go to the far infrared, where conduction phenomena are more important, where the Drude peak is, you are working with wavelengths, which are millimeter sized. So if you have millimeter sized samples, you have less diffraction on the sample. So you would like to have a very large surface of the 2D electronic gas. And the optical thickness is not the true thickness of the electronic gas, but it's the penetration depth. So you would have more signal if you have more conducting layers. So if you get the 2D electronic gas with more carriers in it, the signal will be bigger. So these are the two probably things that you can include to increase your signal. Remember that gated signal is not easy. Probably if you do from the back of the substrate, it's better because you don't want to have an electrode in your optical measurement. Okay? You don't want to, even though I know people say we can put ITO, transparent conductors, it's good for Raman. ITO is horrible. Just a word of caution here, because people asked me to do that. They would put indium tin oxide on top of LAO-STO to gate the LAO and say, hey, it's fine for you. It's a transparent conductor. And then I repeat, it's transparent in the visible, not in the infrared. In the infrared, it's extremely reflecting. It's totally opaque, so it doesn't work. But that would be the thing. Increase the charge density, increase the surface, as thin lanthanum aluminate layer as possible, and that will maximize our chances of having good data.
Thank you, sir.
Yeah, go on. I thought somebody wanted to. Okay. Actually, I have a small question. So two of the other themes of this school will be twisted bilayer graphene,
yes,
and TMD. And I was wondering, I mean, in the case of twisted bilayer graphene, you have flat bands and correlations. So you have sort of a combination of things that you've discussed.
Yeah.
You know of, information that people were able to retrieve using spectroscopy? I mean,
Mark, I mean, I think people have attempted to look already at twisted graphene. There is nothing conclusive on that in optics. The interesting thing on the twisted bilayer graphene is a lot the ability to cover the phase diagram. Essentially of whatever you want, right? Cuprates or pnictides or heavy fermions. Every phase diagram is being done that, every Mott-based phase diagram. But that's done by gating the bilayer graphene, right? So it's a tour de force. I showed the measurement on a small flake of graphene. And I can probably, the major problem of that, I stopped my sharing here mistakenly, so I'll just share it back. You should see my screen, and I just put this back there. So the problem of graphene in the way that it has been measured, so here it is. You don't go really far in the infrared. Okay, so you're stopping the data about here. So this is, and it's already very impressive that they can go this low. This is 1,000 wave numbers. It's 120 millivolts. So this is too high of an energy to look at all those conduction phenomena that you can look in twisted bilayer graphene. I think we will be able to do very nice stuff on that if they find the recipe to make this kind of graphene here. They claim it's almost a centimeter sized graphene layer. So if you can do this, then you can really go into the far infrared and probe Mott physics and probe conduction phenomena. But I think that's the major barrier to get the bilayer graphene, which would be a fantastic thing to look at, actually. Mm. Right. And you had about the other topic, which was?
TMD, so the dichalcogen. chalcogenides, which are also, in some sense, bilayers. But,
so yes, yes, there are many examples. People are looking at that, but it's very similar to the graphene physics.
Okay.
It's very similar to the graphite physics eventually.
Okay, thank you. So are there any more questions or from people? Doesn't seem to be. Well, in that case, thanks again, Ricardo.
Well, thank you very
nice
much
presentation.
For being here.
Okay.
And enjoy the following 2 weeks.